Back up and running.
I didn't hear about this. Oh, okay. So it wasn't
I'm trying to log in, show our calendar.
That's crazy. Holy.
Not 2120. We're here in 3255. Calendar, due dates. So the goal is for today, wrapping up homework number 2, so that Friday we can take a look at any kind of project questions for the New York Stock Exchange kind of data. Yeah, and that's the main plan. Just rolling through. I know this is like midterm season, at least first round of midterm season. So. All right. What are we working on for homework 2?
Yeah. So the last problem, the Monte Carlo one for the rods.
Yeah.
I have a couple questions on that. So part of the problem statement says to make, predict the mean standard deviation for 100 samples with normally distributed R and L. Are we making a normal distribution for L? Because R we're given mean and standard deviation, but L we're only just given 5 meters.
Yeah.
Are we just using 5, or are we also trying to create a normal distributed 100 random points around L?
So because we're using Monte Carlo, we could look at propagation of error of like L, like if L is changing, really Young's modulus, best case scenario is plus minus 10% whenever you measure it. So we could add all those extra random variables, but for now we're just looking at one thing.
So just L is 5.
So L is just going to be a number, and maybe it's plus or minus 1%, like 5 plus or minus a millimeter.
Yep.
But yeah, it could be other shapes.
Okay, so the normal distribution of random numbers is only focused around R.
Yeah,
okay.
Yeah. So we're just looking at the fact that as these things come off the assembly line, they're going to have normal distribution of radii. How does that affect like load?
And then, can you help me understand? I get we can return the mean standard deviation of this critical buckling load.
Okay.
How do we know if something is exceeding that or not? Because it's a 1,000 kilogram structure. Are we essentially taking the 1,000 kilograms times 9.81 and divide it by 100, assuming each rod takes up an equal amount of that force?
Yeah, exactly. So we have like, I don't want to. Let's do this. So we have like 100 rods all holding this thing up, and if we can maintain that only 2 or 3 rods are going to fail, then the whole structure is fine. Like that's our set factor of safety there. So if P critical is more than 1,000 kg times 9.81, no fail. So we have that like main kind of load comparison of like if you're, because if if that critical load is more than the actual applied load, then you're fine. But if it's less than, then at some point, as the structure was loaded on there, it already buckled.
So the critical load is more than that,
right? Yeah, because the like if it's going to fail at 10 newtons, but you apply 11, then it failed.
Whenever the 98.1 newtons is greater than your critical load, that means now that rod has failed.
Yeah, okay. Yeah. So when we look at like the data, there's going to be, if this is our R, this is like number of rods. Have like all the rods have some mean and some standard deviation, and that's going to transfer into like number of rods and then P critical. It's not really going to be a normal distribution, but I mean, if you want to assume that it is, then
that was one of my questions. Every time I did a histogram of P critical, it was skewed.
It skews, right? Yeah.
I don't know why.
Like something. Or wait, it skews right. Yeah, sorry.
Why is that?
Because we're taking R and taking cube.
Okay, so it's making it smaller.
Yeah, it kind of, so if R is small, then it makes them extra small.
Yeah.
Because R is less than 1. Yeah. So if you want to like approximate this, it's like you won't be too far off. You'll be off by a little bit, but a lot of times probably the actual measured critical buckling loads are going to be normal distributions.
So then if you're using the Monte Carlo random method, how do you ensure less than 2.5% fail?
Monte Carlo, the mean, like the way to get Monte Carlo to converge is more. Bigger is better. So instead of just saying like, all right, I have 100 rods, let me simulate 100. You can say, all right, if I have 10,000 sets of 100, now I have almost 1 million rods. Let me look for 2.5% failing there.
But isn't, I mean, the question's asking what length, how do you change the length to affect that?
Oh, let's give it a shot.
Assuming you keep the number of rods the same.
All right, so let's say, do I have, all right, I think I have stuff loaded in. R is RNG dot we can use normal. Zoom in a little bit. Location is going to be R mean. The scale, I think it'll catch up with me. I think it's scale. Is our standard deviation. And then N is N, or size, sorry. Size is N. And then I want to say PCR is I just want to copy this equation in here. NP dot pi cubed times E times R to the 4th over 16 over L squared. I think I got everything. And Monte Carlo buckle. And I have some default values kind of set up in there already. If I look at how I set up my function, Young's modulus, the mean, the standard deviation, because they all have default values, I can just run it without giving it inputs. You can always like specify what the inputs are, but now let's make sure. So mean buckling load.
It came out really large.
That's very large. So I must have done something wrong, right?
You're missing parentheses.
That's what I think. Pi r cubed e r to
16
4
times L squared.
Yeah, over 16 over L squared.
You also have E after the third instead of 2.
Yeah, it should be R to the 4.
R to the 4. That should be R to the 4. Let's try that. There we go. All right, 167. That looks a little better.
There we go.
Yeah. So 167 newtons, but plus or minus 80. So roughly, if this is a normal distribution, then the mean minus 2 standard deviations is going to describe like 97.5% of the data. So one way we can approach this is saying like, all right, mean and 2 standard deviations, that's our like cutoff. So M and S are that. Lower limit equals so like right now, not like formatting it very well, but right now I have 37 newtons. And again, I'm assuming this thing is normally distributed, but it's not really. That's okay. Just to get a sense of how do we deal with these random numbers, and like I know where I want to get to, I just don't know how to get there. And my main design parameter is the length, that I can change the length. So I could say instead of, since 5 is too big, and just to double check, so 5 is too big. So instead of 5, I'll go down to 2. Oh, and have I been echoing this whole time? Sorry. There we go. So go down to 2 meters, and now it bumps it up to like 290 newtons. And each time I run this, it's going to change a little bit because mean and standard deviation are based on random numbers. So if I wanted to change less, I can always make n 1, 2, 3, 4. Like have 1,000 sets of 100, as if I'm running the experiment 1,000 times.
So you're trying to create a lower limit value that's just above the 98.1, basically.
Yeah, yeah.
Because then you would guarantee that less than 2.5%, or not guarantee, but it's likely less than 2.5%.
Yeah, based on
don't fail.
Based on the manufacturing data that I have, that there is a radius. I know it's I know there are random changes to it. So I need to deal with that and decide how tall my structure can actually be if I only have these 100 supports for it. So it's probably somewhere in between. So it's not 5, it's not 2. Cut the difference, maybe 3.5. Now it's 70. We're getting pretty close. And again, there's better ways of like finding a solution like this, but we haven't really covered it yet. That's kind of like coming soon. But if you're, I don't know how, is it bothering anyone that we have to guess and check a little bit? Is anybody else bothered by the guess and check method? Or like, this is where I shine. This is it. But just check. Because we could always say like from scipy dot optimize import fsolve. Fsolve is specifically like a function that finds zeros. So it won't find 98.1, but it will find 0, and it does a great job at it. So I could create a new function called like my optimizer is lambda of L. So the only input is L, and then the output is going to be like M minus. Yeah, how am I going to do that? All right, let's do a definition. So the only input is L, and then the output is going to be mean minus 2 standard deviations. So I'll say throw this into here. So what did I do there? Like, so I'm creating that same lower limit, but then I subtract it from, I take 98.1 and subtract it from there. Why would I do that?
Trying to minimize it.
Trying to minimize it, yeah. Why would I want to take 98.1 minus that thing that I was just... So before, what I was trying to do is like guess and check, keep plugging in an L until I find 98.1. And now I'm saying plug in an L and show me 98.1 minus what I was just guessing and checking. So it would be the same thing as like up here, I say 98.1 minus this whole thing. And it's giving me like a comparison. So 28, so I'm 28 newtons away from what I wanted. And if I get to the point where it's 0, then I have the right L. So that's what, in general, every like computational method is going to give you like some 0 finding method, because you can always rearrange your equation rather than saying like f of x equals 12. You can say f of x minus 12 is 0. And now I say fsolve, if it catches up with me, fsolve of my optimizer, give it some initial guess, anything should work. And I get 5, that one can't be right, right? 4.99? No way. 2. This can't be right. Something's weird. I think because we're using Monte Carlo methods. Because the slope I don't know. Because it can't be right, right? I haven't tried this before, so now I'm... So it's always whatever I give it, it's giving me the same thing back. Weird. Oh, because I'm not changing L. There we go. All right. I do have to plug in the variable that I actually want to change. So that was the problem. Otherwise, it's not going to be. I just have a function that no matter what L I plug in, it's always the same L. So why change what doesn't work anyway? So now, I mean, we should be getting better. But it still doesn't care. It really just does not care about this. I don't know. That's weird. Doesn't seem to matter, right? That's weird. I wonder if it has something to do with Monte Carlo methods, if fsolve, because fsolve usually uses some kind of like some function to calculate its derivative, but it's probably hard for it to find a derivative with like random numbers. There's like a lot of noise in it. Anyway, sorry. I thought there'd be a better way of finding this, but it doesn't seem to. Doesn't seem to want to find our zero here. Well, I guess what I could do is instead I know it's between 2 and 5. I could plot it. I mean, that looks pretty well behaved, right? Derivatives aren't too crazy. There's definitely some zero derivatives in there, depending on where we start, but now I've got like a graph of everywhere from 2, where I'm 100 newtons off, up to 50 newtons off, somewhere in the middle, 2.9 meters in this case. That's that's like the graphical way. But yeah, that fsolve was not working today. Cool. That was a good way to start. Anything else coming up as you're working through? Yeah.
We're just like manually just now like guessing and checking through. That's still like a valid way to do it.
Yeah, definitely. Yep. Yeah, depending on how manual you want to be and how precise you want the number to be, you can set it up to, you can set up your own kind of like solving algorithm, right? Because I could have said for L in L range, and here I probably want to look at like absolute value. So here I could break up, like I created a range of L values from 2 to 5, and I could break that up and say, all right, if it's less than 10 newtons, if I'm within 10 newtons, then show me the result. And I get all these values. The smallest one looks like it's 2.918. And if you want to get even more specific, then just go from like 2.8 to 3 and split that up into 100 sections. But yeah, even this way is still like a guess and check kind of method, because you're manually plugging in a whole bunch of values and then seeing which one is 0. But it's saved, and it depends on how many times you're going to do this. If you're becoming a rod installation expert and you're going to do this another 50 times in your career, then it's worth like making some scripts for it. If this is the one time you're ever going to calculate buckling load in a rod, then do it anyway. Any way you please. Now I really got to look into fsolve. Why it really does not like those Monte Carlo results. Yeah.
For project 2, I'm getting a 404 error when I try to open it up.
Oh, this one keeps coming up for project 2. All right, so in project 2, when you, let me recreate the error that everybody gets. It's slow. When you click this link, it tells you that it can't find that project, but it's there. It's just that it doesn't have this last, oh, not there. It doesn't have this last .md at the in that URL link. So if you put a .md in that URL, then it's like, hey, now I know what you're talking about. And it brings you directly to that project. So there's the files are all, if you click on this like file open, all the files are like in a navigatable kind of structure, and each module has like the readings and homeworks, and then there's a project labeled, or sorry, there's a folder labeled projects that has all the projects in it. But if we want to fix this, then we'll do some quick editing to this. So the structure of this link is that everything in blue, the bold blue, is the text that describes the link, and then this is a hyperlink, like a local hyperlink, telling you to like go to a certain file location. So we'll add a .md to there, and now it matches where we want to go. A bonus Easter egg hunt for the project. Learning a little bit of Markdown, file location, hyperlinks, all sorts of good stuff. But that's how we can get there for the project. Like it looks like you're taking every What is their 90
I know.
Yeah, like right now.
Did you do?
With this,
Did you get through the
this
This is taking the year.
We're so far in
So I have to go get the first one. What I did was I was saying,
I went to ChatGPT and I was like, make this a definition. Make this a function.
Oh, really?
And how could
I started by making a function.
What is
I ended up using ChatGPT to basically like, hey, how do you use DMT solve basically and confirm that I got your right.
yeah.
So it's right. No, I checked it through ChatGPT like, hey, this is the answer I got for number 2 or 3. Here was the question I'm able to solve. And it worked.
It looks great. Yeah, but what data? Yeah, yeah. I mean, it's like it's taking all the data and showing everything all the long time. It's just, it gets confusing. But I think there's 50 different entities in there. US is like and for Canvas data frames, whenever you print, it tries to put it into like new text. But if you just use the right energies, then there's a nice like pretty print for it. Yeah. So now it's showing like the table, and there's even like this one. You can organize it by this data is the same. It's just yes. Yeah, it doesn't look good when you print it, but it just shows up these things.
Really? Yeah. Give me a second.
That one,
No,
so
it is.
this is great because now you just have an array of values in it. So you don't have to worry about data frame syntax.
No. There equals something. You need to get in there because then it's going to say the first one, but you need to.
So you like US instead of
You say check monitor? Go to more
yeah,
It's just like I got this chunk.
So you know it's called
There's some of the items you see they're good, and the other ones are funky. There's a zooming out reaction. Once you get the data, you just green space.
It's just going to be red.
And also ran the actual data sets to make sure they were doing what I thought they were doing.
Okay. Yeah. Like I don't know what these Oh yeah, that's one of the things don't understand. Always keep them.
So basically,
It's close enough.
but I also I wrote videos of code. It would tell me the frequency and where it is.
Respectful.
So you go here, the except two will tell you the frequency and amplitude and how it shows up on here. So you don't guess.
Yeah, I'm sure that they're all right. I'm sure you know about them. I like that video and then use that FYI and then leave us there.
So basically,
Instead of
you're basically your final program.
and try and just
And then you go up truncating pieces of it. So then basically one of the frequencies and that frequency domain.
Okay.
So what it is basically saying, I'm going to do
Yeah.
and I'm going to say anytime this final has a something that's greater than
And
because you can use it like
to use
but
so it goes
so anything that's greater than that, you're basically want to do two lists.
if
I
you
want
want to try
what the hell you should do and also want to and then you just index the frequency channel and the amplitude is the value. So for instance, that first one,
It's not too bad. It's just I didn't know what's wrong.
because that's the amplitude you find first.
I just have some questions about like what this is really doing. So what is the low line saying? This is
So in this first one, short index, amplitude
I just had to read it down before. Okay. What I understand.
so it's going to give you,
So
you
we're
multiply the
looking for this
index
F,
times the
right?
frequency,
Yep.
gives you
Okay.
your true frequency.
And
amplitude.
so this is the one I was reading.
2 hertz. And then again, you put in,
But
and then you can also, when you
so
plot
we're
it,
looking for this to be 0.
you can then do an if statement when you want. So you do PLP amplitude, and you basically say,
In which case,
you look back at that, these frequencies and amplitudes, and you can plug in the XY coordinates based on the index. And so it'll pop up.
Why is this
Peaks are-
98.1? Like, I don't understand. Go back to the my first question. Why we got numbers at 98?
So basically, so
we have what you want to say.
so this first one here is the,
Okay.
is what is the label belongs to something. So basically, I want, the format, I want the frequency, the combined frequencies, and I want to find at 1% index, so it's however many there are. So starting with 0.
So that's where
that,
the first instance. I
This
want
is telling us
the frequency, which is
pretty
going
much
to be
how
X
much
value,
like
so it's going to be the Y value.
on it. So
Then
we want.
this is
So this is
location,
telling like how much
where you want to
around that value
This is the location of the
is
data
the
point you want to select. So then this is just
So yeah, I
the
didn't
frequency
change
and
my
amplitude
grade
0 0.
Really,
And then this is the like the XY offset of the
if I'm assuming that it's
actually it's the Y basis.
I just want to find that lower tail.
And it loops to it, so no matter how many of these you have, it'll loop to it.
2.5% are going to be less than mean minus two.
That first, this back to this first one here, the rest of the component frequencies are only going to look at the ones that are greater than 0.1.
So when I say the lower limit,
For instance, if I were to return, so if I were to return,
the comparison that I'm trying to make, if it's 98.1,
basically this F,
then I can build
this is my final array. If you truncate all the
more
data,
than
this is what it's plotting, this F final.
over designing.
What you have here is saying,
It's 10 centimeters tall, but it's made it 2 meters tall.
yes, same concept, same exact concept.
And then if it's less
That's
than
what this
that,
is plotting. And then I'm saying,
if that limit is
let's look at all the data points in that array.
me
Let's find the
minus
ones
2
that
centimeters,
are greater than 0.1,
and
because we can zoom on one of them.
main structure really tall,
Then you're going to say, all right,
then
what's this
going to
the
be
amplitude value?
most of the
Put that on this. You're going to say, what's the index?
So we're figuring out.
And the index is going to be multiplied by the frequency, because every step is n times the frequencies.
yeah.
Four
And
times
when you say things like that,
which is 2. In this case, is 1.5. move through
I guess
all
that's
the
what
ones
we
that,
get through.
where that exists.
I know, yeah.
It's cool. I need to figure out what fun.
Yeah. Easier to like people touch on things.
Basically, like, I got to the end and I started like doing answering questions. So, like, I don't really understand why the shift in frequency there. Explain it to me.
Oh, it's basically just saying,
You're taking more samples.
So like, there's less of a chance for you to see the actual frequency that they're leaning on.
Yes, exactly, and it's a source of data, basically. If you don't have a sample, if you don't have a high enough sampling rate, then frequency, you know, to do that source. Yes, there was something like that where you had to be twice that. Your sampling rate.
Two times frequency.
Is the highest, two times the highest frequency has to be your minimum sampling rate, and the highest frequency is 200. And when you sample that, it's 250, so it's not going to capture. Yeah, I spent that.
That one's to pay on.
No, so exactly.
It shows, it means that if something.
Because again, it basically the question is, where do you think these are? So that's where I did the board loops.
And then
There's definitely
and then from there take the greater than point one.
Yeah.
And then do a great like troubleshooting. Sometimes what happens.
But they haven't posted a lot of third question. Yeah, it's like you're out there. What you expect to see, like, it's just crazy though. Like, if you don't know how to you're screwed.
1, 2, 3, 4, 3, 1.
They kind of like first few years.
Well, I knew what I wanted.
First, I started just writing the first one. I'm just
Right.
That was all I had.
This one, this question.
Oh, speak for yourself.
You did that one?
Yeah, take a picture.
So if you don't put it in sample rate, it's all
I didn't even build it. Just reading the file. I should have put that in there. I could clean it up basically. But actually, no, the thing is, I want to copy the original data. But the problem is, how do you want the responses you verify? Because if you have to guilty.show. Now we're getting
Figure, so we have to
Yes.
figure one out. And they'll pop them both.
Wait,
Yeah, every time I try to pop both, it would just override it basically.
If you have a line, right?
It's fine. So the linear regression
Okay, so you label them.
I've done some laws, but yeah. We thought that. I disagree.
It hasn't cleaned up, I chose to. It works now. All I want to do is allow them to be nice. Plug in the file name and say, and then boom. Yeah, actually, I could technically read the file, I could read the length of the. No, you have to know. No, it's here.
Yeah, because the length is actually also important.
The length gives you numbers, and that's usually easy.
So when I was plotting, when I'm plotting,
Very good.
you can try that. You can try it. Yeah, linear on a long scale. So it is a straight line, and it's e to the function. Yeah.
Is that really the function? Okay, fair enough.
Everything here is below 100. Meanwhile, every transmutation of 70 is at 1,000.
This is similar.
There's something order different between your stuff versus
You. You do. I wish I did. I didn't know this one.
So right now, this is kind of a weird way to look at data. This number is e to the because we took the log out. I would love that data. All the pieces are there. It is a linear plot. It's just that it's linear on e to the something scale. So we just put it back. Like we put that linear exponent of that linear. We now get that. Yeah. That one might work. But you know,
Yes, you absolutely do. I think I've seen users that's for the assignment for the quarter.
That was for my iCard
Super
secret security clearance project I'm working on right now. Yeah, you remember that.
Thanks for joining.